So in this session, we are going to discuss about initially the evaporator auxiliaries. You see that many evaporators which deal with the heat sensitive material, we cannot go on increasing the temperature indefinitely for more vaporization. And at its boiling point, maybe the water's boiling point in the solution, the utility value of this solute or the overall solution may be lost. So under this condition, we have to create vacuum, right? Additionally, if it is a multiple effect evaporator, where we will discuss that. So we can mostly have multiple effect evaporators where we have to increase the steam economy above and over that one. The steam economy, as you know, it's defined as the amount of steam vaporized or amount of vapor generated per unit mass of the steam used. So if I have to increase the steam economy beyond 1, right, which in case of single effect evaporator is less than 1, we have to switch to multiple effect. So in multiple effect, the fast effect may be operating at 1 atmospheric pressure. But if I am using 3 or 4 effects subsequently, then the pressure must be decreasing, right. So in the last effect or last but previous, but and additionally for these last 3-4 effects or last at least 2 effects, we have to operate them in vacuum. So what will be the vacuum generating device in this evaporator drum? So for small evaporators, see, we are discussing here the evaporator auxiliaries. The first one is vacuum creating device. So you can use here for small scale operation the vacuum pump, right, but more of high utility and this is of higher economy, that is steam jet ejector. Right. So vacuum pump, mostly you see it is a kind of reciprocating pump which undergoes a to and fro motion of piston in a cylinder, and these vacuum pumps may be operating in wet or in dry basis. In dry basis, the vapor directly enters this pump cylinder, whereas in wet basis there is a surface condenser intermediately. The vapor is first converted into condensate and then the condensate enters the liquid, this pump, right. So that's the wet centrifugal pump, and generally if properly maintained and designed, the reciprocating vacuum pump's efficiency can be expected to be pretty high. But these are restricted, the vacuum pumps, its operation and utility is restricted for small scale operation. For large scale operation, for industrial large evaporators, we have to go for steam jet ejector. Now, as you know that we have discussed this steam jet ejector a bit, where we were talking about these non-mechanical pumps in fluid mechanics. Here we will go for it in detail and we will be discussing a ejector system which is a 3-stage steam jet ejector. Now, you see, here we have the first stage. This entry is connected to the evaporator drum. We have the delivery of or the external utility which is required to operate the steam jet ejector is a medium pressure steam, right, 5 to 6 bar pressure, and these steam which enters into the mixing chamber through highly converging nozzles, right, like this, a series of highly converging nozzles. Let me draw it first and next I will explain. So, subsequently we have a direct contact condenser, right. So, this direct contact condenser it has got this contacting plates, deflector or contact baffles, whatever you can say, and from here the condensate comes out through a long tube which is called the barometric leg, right, delivering the liquid into an open container which is of concrete structure. It's called the hot well. So, you see this hot well is partitioned into two chambers. Why we will discuss. And from here we deliver it to cooling tower, right. So, that is the barometric leg. First, let us understand the construction, right. Its height is 34 feet. This is the direct, or in this side let me write the direct contact condenser. This is the mixing chamber. Diffuser, and here we deliver this water, right. So, here this is the cooling water line. From this, the incondensable, it enters the second steam jet ejector. And you see there is a structural integrity which we must use for a compact design. What is that? It enters the upper part of direct contact condenser or the second stage. It seems to enter, but actually it is going where? There is a block, and from here it goes to the third stage. So, from here we have the second steam jet ejector, right. Here we again have the same steam, MP steam, and the nozzles. Right. From the outlet, it goes to the second steam jet ejector. Again, there are baffles and all. Now, from this stage, it goes to the third steam jet ejector, which is smaller one. Right. Again, medium pressure steam is delivered. The nozzles are there, and the diffuser and mixing chamber. Right. So, cooling water So, this is the cooling water line, and it must be delivered here. Where it splashes right here. So, from the bottom of the second stage, there will be again a barometric leg giving the output in the first larger chamber of the hot well, and from here the two phase goes to this part, releasing the vapor plus liquid in the second chamber of the hot well. So, this is the hot well. Its temperature will be around 55 to 60 degrees Celsius, and you see this is the second stage ejector. This is the third stage ejector, and again a direct contact condenser, right, and this is the first stage ejector. Yeah. So, from here the vapor and non-condensable goes to the second stage. So, you see what happens. This is connected to evaporator. So, when we charge high pressure steam, and as these are converging nozzle, over this region P is lower than atmospheric pressure. So, naturally it will suck the material from this evaporator, and here in this mixing chamber it mixes properly, and the diffuser section slightly increases its pressure. So, mixing chamber and diffuser actually promotes this entire process of mixing. Now, next this two phase, because or actually it is a single phase, it enters into this direct contact condenser because it is water, this is steam, right, it is water. So, we can have a direct contact heat exchange. So, we are increasing the heat transfer and contact time by inserting these baffles, right, and here we have the cooling water supply. Now, we have the formation of condensate, right, and the condensate is to be released. Now, you see that if we directly release the condensate into atmosphere, the vacuum will be lost because the air will gush in, like if I cut this pipe here. So, this is inserted in a pool of water, right. Now, which is exposed, this is exposed to atmospheric pressure. Now, if I have pressure here, against the pressure, against atmospheric pressure, the water can maximally rise up to 34 feet. So, that is why the barometric leg must have a height of 34 feet, such that there will be no backflow of this water here or in this region. And the next stages are all identical. From this first direct contact condenser, it goes to the second steam jet ejector, where from again the vacuum is intensified and the vapor non-condensable is being fed to this second direct contact condenser, or alternatively called intercooler, right. From that it enters into the third stage. Now, we cannot go on maintaining the first, second, third direct contact condenser. So, from the small steam jet ejector itself, it is being fed into the second chamber of the hot well, actually you see that when the condensate is being released, this will overflow like from first chamber to the second chamber. And if you look into the detail, what is the structure of this overflow? There is the partitioning wall, right. So as it overflows, it creates a space which is being covered from this side by the jet of water, and on these two other side there will be the solid wall, right. And in this space we are discharging the outlet of the third or the last stage of this condenser. So automatically whatever condensate we have or whatever uncondensable we have, it will leak through and the steam it will condense and precipitate out. From here we can feed it to the drain, or alternatively if we wish to recirculate back the cooling water, we will feed it to the cooling tower. So that is the structure of steam jet ejector system, right. So for small evaporator we must go for vacuum pumps, whereas for large evaporators it is the steam jet ejector. Now next, as I have mentioned that in the condensate outlet of all evaporator, we must have a special type of valve called steam trap. So I will not go into the details of the steam trap. Steam trap is a valve, right, is a special type of valve which will allow only the passage of the condensate, that is a liquid, right, without allowing steam to flow out. Okay. So steam trap, generally there are different types of the steam trap, mechanical, thermostatic, thermodynamic, etc. So it operates either based on the principle of density difference or based on the this temperature difference, because once the condensate is formed, for theoretical calculation we do not consider any temperature change, but actually once the condensate is formed there is a temperature change of 1 to 25 degree, right. So there is a difference of temperature, there may be a difference of density, there may be or actually a difference of flow properties. So based on in these properties, if we design a valve which will allow the passage of condensate, that is a liquid, without allowing the passage of steam, that is a vapor, that becomes a steam trap. And generally we explored the property difference between the steam and the condensate, and that difference may be the density difference, may be the difference in temperature, difference in flow characteristics, etc. Now next we will go for entrainment separator, right. There are two different types as I mentioned. One is demister, another is catch-all. So you see, demister itself is a thick pad of wire mesh like this, right, mounted close to this evaporator outlet. This is mounted close to this evaporator's vapor outlet, and this is the pool of liquid. What will happen? And we have support, it's circular cross section, right. We have this T-angle circular beam on which it's resting. So you see that whenever the entrant liquid droplet and the vapor passes through this wire mesh, what will happen? Because of interfacial tension, the liquid droplet will be trapped within the cage of this wire mesh, and definitely it will coalesce with adjacent liquid droplet and fall back to that liquid pool, whereas the vapor will pass. So that is called demister. Here definitely what is the problem? If the evaporator section is large, then there may be intermediate sagging of this demister. So in that case we have to put these I sections beams here for support, proper support of this demister. Next, the catch-all. See, it's an external device. So demister is internal to the evaporator. where catch-all is external. Here from this vapor outlet, it goes to a chamber very similar to cyclone, and we have the vapor, final vapor outlet line inserted deep into that chamber, and sorry, here it should be, the entry should be somewhere here, it's tangential just like cyclone, and we have helical baffles. Right. So, this is the helical baffle. What will happen as the liquid moves? So, it will follow a circular descending pathway, right, and as it moves like this, because of higher density, the liquid droplets will be thrown outward and finally it will be collected from here. So, liquid, and here the vapor, after descending, it will move up through the central line, that is the vapor outlet, right. So, this is called catch-all, used for as an alternative to demister. The demister is an internal device, whereas catch-all is external. So, next we go for principles of evaporations and evaporators, and there are some terminologies and phenomena we have to understand. So, first one is called capacity of an evaporator. Right. The first we will discuss about the capacity, and next we will go for steam economy. So, what is capacity? Amount of vapor generated per unit time in kg per hour. That is called the capacity of an evaporator, right. And steam economy kg of vapor generated per kg of steam used. That is called economy, which is less than 1 for single effect and greater than 1 for multiple effect. Right. So, capacity and steam economy, these are very important ideas related to the evaporator. The steam economy is somewhat related to the efficiency of this evaporator, right. So, next one is boiling point elevation or boiling point rise. You see, the boiling point, let boiling point of water from a solution Ts. Now, pure water's boiling point is Tw at the same pressure. And it is very obvious from the property of the solution that Ts is greater than Tw, right. Ts is greater than Tw. So, this is a very well known property of colligative property like osmotic pressure, depressions of freezing point and all. We will not go into that this thermodynamics of this system. But what is important, this Ts is greater than Tw, and over a wide range of Tw, that means which is dictating factor is a pressure, right? Pressure actually changes this Tw. So, for over a wide range of Tw, we know, or it has been established, that Ts is a linear function of Tw, right? For a wide range of temperature and pressure, of course, or for a wide range of pressure, basically. Temperature, we should not say that because pressure dictates the boiling point. Ts is a linear function of Tw, right? So, Ts is equal to A into Tw plus B. So, this is called During's theorem. Right. So, you see that respective plot of Ts by Tw, that is called the During's plot. During's plot. How it looks like? Say it is Ts and this is Tw, and over certain region of very low temperature, right? So, everywhere this is for pure water. Everywhere we see this sort of straight line kind of relation. And these lines represents different concentration, right? Just like this is pure water, this is 5%, say sodium hydroxide, this is 10%, this is 15%, 20%, so on and so forth. So, what we see that for different concentration, slope of Ts versus Tw plot, that is A, remains nearly constant, right? While B, the intercept, B changes, right? Definitely there is some initial region where the linearity is not being maintained, but after that we have fairly accurate linear curve, right? So, this is called the boiling point elevation. So, basically you see the boiling point elevation we write as Ts minus Tw, Bpe. Okay? So, this boiling point elevation we can easily find out from During's plot provided we know the pressures and the concentration of this solution what we are treating. So, if this is the concentration, say it is 5% and we know this pressure, so we can get these Ts from During's plot. So, naturally as this boiling point changes, there will be, so this is the boiling point change. Next there will be change of latent heat as well, right? So, you see pure water's latent heat is lambda W, latent heat of water from a solution is lambda S. So, what is the relation? This is known as During's equation. what it states? Lambda W divided by lambda S is equal to delta TW divided by delta TS into capital TW by capital TS whole square, right. So this is referred as During's equation, okay. So you see this entire thing is what? dTW dTS, so inverse of the slope of During's plot. Like for this specific case where the solution concentration is 5%, we have the straight line, we have got Ts. So here we can find the slope, right. So 1 by slope is equal to delta TW by delta TS, and that we will directly substitute here. We know lambda W, so we can find out lambda S, right. So this is During's equation. Similarly, the alternative equation is Othmar equation, but During's equation is fairly accurate for different types of system, right. Next you see that the next important terminology here, or phenomena rather, is a boiling point elevation or boiling point rise because of hydrostatic head, and that we refer as correction for hydrostatic head. What is the case? Think I have a calandria type evaporator, right, and this is the tube. Now evaporation somewhere, the vaporization takes place here. Now at this point the boiling point is Ts, right, what we have calculated from During's plot. Now here what will be the boiling point? Definitely it is under the additional pressure of this Z, right, the height is Z. So the vaporization or the boiling is taking place at a height or at a depth Z below the free liquid surface, and let us say that at this surface the boiling point is, let us say it is Ts prime, right, so which we have previously referred as Ts, right. So boiling point of water from a solution at free water surface with pressure P. So here the pressure is P. So under this condition, at this point it is the Ts prime. Now additionally, because of this Z, there will be a change in boiling point, and that we refer as hydrostatic or correction for hydrostatic head Th, right. So true boiling point, so actual boiling point is Ts prime plus delta Th, which is alternatively BP boiling point elevation plus Tw, right, that is Ts prime plus delta Th. Now this additional pressure, the effect of additional pressure, we can easily solve from, or theoretically we can solve from Clausius-Clapeyron equation. However, the point is, because of this additional pressure, what will be the boiling point? We can find out from Clausius-Clapeyron equation theoretically, but Clausius-Clapeyron equation is inaccurate, right, as we move from triple point to critical point. At critical point, this latent heat of vaporization is 0, at triple point it is maximum. So Clausius-Clapeyron is valid close to triple point, right, but as we move along the vaporization line towards the critical point, the validity is being questioned, and it is more and more giving you inaccurate results of this outcome, that is the boiling point elevation. So there are empirical relations, right, which you do not have to remember, but that empirical relation states, it is given in the book of Kant, the TH is equal to 0.06 TR into V divided by lambda S into Z. This is a equation in FPS system. This is in degree Fahrenheit. TR is TS prime expressed in Rankine, right? V is the molar volume of the vapor. So it is feet cube per pound mole. Z is in feet, and lambda S, as we have solved, it's in BTU per pound, right? BTU per pound, okay? Lambda is latent heat of vaporization of water from the solution in BTU per pound. Z is the hydrostatic head. So we have solved the problem of elevated temperature or elevated boiling temperature, changed latent heat, and we have also included the hydrostatic head, right? Now next point is the heat transfer coefficient. So heat transfer coefficient, or rather the overall heat transfer coefficient, you see it's entirely defined. Actually, if I write that overall heat transfer coefficient equal to, neglecting the metal wall resistance, HO plus 1 by HI. So HO is the external heat transfer coefficient. We can get it directly from Nusselt equation, right? Because we have mostly these tubes, and over that this vertical film is being formed, right? And Nusselt equation for vertical pipe, this average 0.728 or how much exactly I don't remember, 0.943, right? Let me check once again. Yeah, 0.943 kF cube rho square G into lambda divided by mu into delta T into L whole to the power 1 by 4. So that's the Nusselt equation by which we can solve it, right? So huge uncertainty is in question because of HI. Why? Because it is a two-phase, right? So here internal to the tube, here we have bubbles or small bubbles, then larger bubbles. Mostly these larger bubbles, sometimes it's vapor slugs, and that is being released for short tube vertical evaporator maybe, right? So it's a two-phase system with a very complex hydrodynamics, and that's why we have to rely on previous data or experimental data, right? From experimental data we have to actually calculate or actually get this heat transfer coefficient. However, if it is natural circulation, this is the case for natural circulation. In forced circulation it's pretty easy, because in forced circulation it remains as liquid. For forced circulation we may use C dot Tate equation, right? So by C dot Tate we can solve, because there is no vaporization, no two-phase generation. So simply we will use C dot Tate. So approximate range of this overall heat transfer coefficient, you see U is equal to around, what is the range? 750 to 2500. This is in kilocalorie per hour meter square degree Celsius. So, this is for short tube vertical. For long tube vertical it is 1000 to 3000, right. For falling film it is 500 to 2500. So, you can understand that long tube vertical has got a much higher heat transfer coefficient, overall heat transfer coefficient, that the short tube or falling film, which we have discussed, because internal to the tube its full vapor generation, there is a tremendous volume flow rate enhancement, and as a consequence we have a very high velocity. So, next you see that another parameter is there, which is the specific heat, right. Specific heat of a solution, right. It is different from the specific heat of pure water. So, how to calculate, how to determine the specific heat of a solution, right. So, there are several rules. See, the specific heat of a solution is decreases generally, right. It decreases with the increase of concentration of the solid. So, if at concentration x1, that is the mass fraction, the specific heat is Cp1, then Cp2 will be equal to Cp0 minus Cp0 minus Cp1 into x2 by x1, right. This is simply a linear interpolating relation we are considering here. So, that is one way of getting the specific heat. Definitely there are other ways. This is an approximate equation, that Cp equal to Cp0 into 1 minus x, where x is less than 0.2, right. Specific heat of a major solvent. And third is Cp is equal to Cp0 into 1 minus x plus anhydrous solid specific heat into x. So, for anhydrous solid, if we know the specific heat, definitely we can get a tentative value of Cp for the solution. So, this is a kind of linear combination we are using here, right. Most commonly we have to, we generally use this, where we have to know at least one specific heat for a specific concentration or mass fraction. So, additionally we have more accurate Cp versus x table, right, or plots which are available in design books like Ludwig or in Karn. So, that is about the specific heat. So, next let us discuss about the material balance, energy balance and the capacity equation of a single effective evaporator. Material balance, energy balance, wherefrom we can solve for its heat transfer area, right. So, you see it is a single effective evaporator. It is a schematic of a single effective evaporator. Let us say the feed flow rate is F, concentration ZF, its temperature is TF. Vapor flow rate V, Y, which we assume to be 0. And here liquid flow rate L, composition X, the pressure P, pure water's boiling point is TW. We are feeding steam at a flow rate of m dot st, its latent heat is lambda st, right. So, what are the assumptions? first no superheating or no subcooling rather of condensate. Right. Second, y is equal to 0. Third, no heat loss. Right. Anything else? A steady state, obviously, no heat loss, no entrainment, only latent heat is transferred. Fine. No entrainment and what I have mentioned? Yeah, steady state. So, it is a kind of steady state analysis. So, you see that overall material balance is very elementary. F is equal to V plus L. Next, the component balance FZF is equal to V into Y plus L into X. Now, Y is equal to 0. So, FZF is equal to L into X. And energy balance. So, let us say we know pressure, we know TW and average concentration. If we do not even assume this, it is a typical continuous start system, which is actually not. Here over this region the concentration is ZF, here the concentration will progressively decrease, right. So, at steady state average concentration we can write some x bar is equal to ZF plus x divided by 2, some average kind of concentration. So, average concentration as we know, or we can go for highest concentration, let us say it is x is specified, right, x is specified. So, at x, knowing x and knowing pressure, we can solve first from steam table TW. Now, from TW and x using During's equation we can get Ts prime, and considering the design of this heat exchanger or type of this evaporator, like whether it is a short tube vertical or long tube vertical, we know what is the pool height of liquid and from there we can get Ts. So, from what we are getting here, you see from P to TW. So, this is we are using steam table from TW and X, the liquid concentration. We are getting Ts prime and we are using this During's plot. From Ts prime delta Th we are getting Ts, and additionally using During's equation we get lambda s, and lambda s is to be used here in order to get Ts according to the structure of this empirical equation we have discussed, right. So, knowing P we can finally solve for Ts. So, next the energy balance, you see there are two heat load. If first the feed is to be heated, Cpf is the specific heat of the feed and which we know how to calculate, right. So, feed is to be heated to the boiling point. So, F into Tf, Ts minus Tf. So, this part is subcooled heat load, right, plus V into lambda s, latent heat load. That is the total heat exchange Q dot, right, total heat flow rate basically into the system, which is being delivered by the condensing steam only, m dot st into lambda st, right. So, first is the overall material balance, second component balance, third energy balance, and fourth the capacity equation, right, which is Q is equal to U into A into TST steam temperature minus Ts. So you see that unlike heat exchanger where we have to use this LMTD, here this temperature is TST and here the liquid is boiling, so temperature is Ts. So the driving force is fixed, it is not varying from here to here. So it is TST minus Ts multiplied by U into A, where A is the heat transfer area, U is the overall heat transfer coefficient, gives you Q. Now what will be given to you? In a design problem, what will be generally supplied? F will be given, ZF will be given, TF will be given, and target concentration will be given. Right. So 1, 2, 3, 4, 5. Sorry, 4. And what we have to solve? We have to solve for area, we have to solve for m dot st, we have to solve for L, we have to solve for V. Now you see, F is known, ZF is known, right? F, ZF, that's known, right? We know X, and from we have to fix certain pressure. Generally for single effect we can use this atmospheric pressure, but if it is heat sensitive then we may go for vacuum. That depends on the specific type of feed and my operating cost, allowed operating cost, right. So from there we can fix the pressure. Once we fix pressure we will get TW. Once we get TW we have the concentration of this concentrated the outgoing liquor that is known, right. Using During's plot you will get Ts prime, and additionally using During's equation we will get the lambda S. So knowing lambda S and Ts prime, considering the hydrostatic head correction, we will get Ts, that is the true boiling point of the liquid in this system, right. So we know F, we have got ZF, we know X, right. Cp can be calculated, Ts calculated. So how many, if we simply eliminate this Q, right, and here we write m dot st into lambda st equal to this, we have 1, 2, 3 and 4 equations and we have 4 unknowns to solve, right. So we can solve it, and from there we can actually get the heat transfer area, right, heat transfer area necessary to perform the given duty, and that is the and the steam flow rate definitely, and what liquid flow rate and what vapor flow rate also we are getting, that also we can solve. So knowing the area, next we have to start the mechanical design. Definitely we are not discussing here in this specifically from the perspective of GATE, there is no question of getting into the specific equipment's mechanical design. We will discuss the mechanical design in general later, right. So that's all about the single effect evaporator, okay. So in the next session, see, in the next session we will first discuss the different types of this multiple effect, and that includes forward feed, backward feed, mixed feed and parallel feed, and after that we will discuss about that how to design a multiple effect evaporator. So that will be all about this evaporator as process equipment. Thank you.